Okay. Um, just a few reminders. Today is not March 2nd, 2015. And I'm not David. So don't take this information as accurate. David is out of town, so I'm covering for him today. So we will do a little review of what we've seen and maybe some new topics and some questions and answers. So feel free to, as always, ask questions. Before we begin, I got a request to change my office hours to a later time. How many of you would support that idea? How many of you are against the idea of changing the office hours to a later time? 1, 2. Okay, I haven't seen you. So my office hours are on Wednesdays at 2 p.m. Just a reminder. So does it sound good to switch it to a later time, like 4 p.m., maybe 5 p.m.? So the problem is availability, classroom availability. If I can't find a class in this building, we'll probably have to do it in the Center for Data Science. I could do Wednesday later, 4 or 5 p.m., or I could do Thursday later. Any preference? Yeah, sorry?
5.
At what day? Wednesday?
5.
Wednesday or Thursday? So Wednesday 5 p.m. you have another class. Okay, just let me note that down. So it has to be before Wednesday. So Wednesday 3:30 p.m., Wednesday 4 p.m. are options. What about Thursdays? Do you have class after 3 p.m. before this time?
Actually, events are on Thursday, so it might be better Thursday.
If what?
I said professors,
Yeah.
are on Thursday, so maybe
It's after this time though.
yeah, so maybe it's better Thursday.
It's at 8 p.m. But graders have office hours on Tuesdays, so Fridays are a bit tricky. Yeah, last semester I tried Fridays, nobody seemed to join. Wednesday 4 is fine, okay. Okay, maybe I should do a poll. Okay. Oops. Yeah. So, how do you tune your system when you do your homework? It's usually by inspection. You try a few things. Usually the first things you try don't work, so you have to tune it again, right? It's either too small or too large. If it's too large, it oscillates, it gives you random numbers. If it's too small, it just doesn't move, it doesn't improve. And then you find the sweet spot, and then you zoom in. Once you find the sweet spot, and you zoom in, you play around in that region to find the optimal place. How do you check something is optimal? You know, a hyperparameter tuning is optimal. You check it by the improvement in the validation set. Because we don't care. We can always make the training set have very low energies, very low cost. But it doesn't make sense if it doesn't correspond to an improvement in the validation set. Validation set can be thought of as a generalization, how well the machine generalizes. If it doesn't generalize well, then it's memorizing. It's memorizing means it's overfitting. Overfitting is something that we don't want. So we monitor the validation set. Or if we have the test set available, we can do that. But technically, the jargon is that you screen the validation set. Have you had any trouble tuning your systems in your homeworks?
Takes time.
Takes time. Well, what other issues have you got? Yeah, that's an issue. But if you really need to go below double precision, then maybe something is wrong. Yes? Mm-hmm. 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 It's possible. I didn't actually check what's going on with homework because it's a separate thing. But I can look it up if you have the definition of what exactly is going on there. From a general theoretical point of view. In practice, I would start with a small step size. I would increase it little by little until it diverges. So the moment right before divergence is your sweet spot, typically. Yeah, it depends on how you set up the regularization, right? So if you we're gonna do it in a few slides. If you set a really small lambda, then the regularization doesn't have any effect. That's why you need to start from a large lambda value. But it again depends on your particular setup. So most of the times, but you should also be careful because if you set up too much, if you increase lambda by too much, then the object that you're optimizing is the right-hand side, is the second term, is the regularizer term, which is also, which blocks you from dealing with the original task. Original task was the actual loss. So the additional term shouldn't be too large as well. It should be a meaningful value. So for example, if you have some cost plus some regularization, let's say it's parameterized with W, say you have something like this. Okay. What happens if you pick a very large lambda? What happens? It becomes 0, right? Why does it become 0? Because this term is meaningless after some time. The only contribution, so the optimization, your parabola is going to be something like this, and this little cost is maybe just a tiny bit noise around it. So once you optimize, bam, 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 in a few steps you come to a 0 point. But this is your task. You need to focus on this. So, but what happens if this is too small? If this is too small, you just optimize this, then it's not regular. So you don't punish with very exploding values of entries of the parameters. So for step size, I would start from a smaller number and increase it. For regularization parameter, I would start from a higher number if I know what the solution is, and then decrease it to find the balance between the two. Did you have another question? Okay. Yeah. 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 That sounds like it's something that fits to this intuition. That's something that you're probably familiar with as well. Sometimes you want to compare two different methods, and it seems like they just go down, and then it seems like they both make this shape, so it's not differential. You don't really know what's going on. But once you take the log scale, then you realize what's happening here is actually something like this with, let's say, stochastic gradient descent, and maybe something like this with the gradient descent. So this little gap that was non-existent before in this plot, in the real plot, it becomes visible and noticeable in the log plot. Okay, some loss functions. So suppose we have the total loss. We don't average it. We don't divide this expression of j of omega with n, with the number of samples. Then what happens? Gradient calculation is easy. Since differentiation is a linear operator, we can take differentiation operator into the sum, which is a finite sum, so we can do that, right? We can switch differentiation with the sum. If it were an infinite sum, then I would have to check whether it was converging uniformly or not. But it's a finite sum, so I can do that. I switch the order of differentiation with respect to summation, then I get the second equation, which gives me the gradient. Then I can follow the path of the gradient, simple enough. So from this expression of the gradient of j of omega, what is the step of stochastic gradient descent? And that's the last equation, last line, actually. There's no equality sign there. So the last line tells me that if I want to do things in the stochastic way, then I would have to take a step in the direction of -2 times w parameters times input minus the output times input again. It's going to be a vector. This dot product is a number minus a number times a number multiplied with a vector. But how do you compare the derivative here and the derivative there if you don't have the averaging? What differentiates them? What's different between the two? True, but if I had 1 over n, that would be still true. So I want a difference between the two that's only particular, to the choice of the factor 1 over n. Direction? Well, it's just a scaling, so I can add 1 over n and I get the same direction, right? Think in terms of magnitude. What's the difference between the gradient of j of w? So what's the difference between the gradient step versus the stochastic gradient step? The divider?
It would be larger.
Yes, it will be larger, right? The first one will be much larger because I take gradients and I add them up. I add n different vectors. So this one is addition of n different vectors. Imagine little vectors here, 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 here. Maybe they rotate and come back. I don't know that. But in the end, on average, in the expected value, right, in the sense of mean of things, it's larger because in the end, I'm adding n different vectors, and this is going to be the total one. Then those are the little steps. Right. When I take the average, if I look at the gradient, let's erase this one. So if I had this 1 over n factor in front of this expression of minus gradient j omega, then I would have this vector, this is the total gradient, and divided by n, right? There's n of them, so it's, let's say, roughly somewhere here. That would be the average one. So in terms of how big of a step you are taking in that mountainous landscape, the scale of the two are very different depending on whether you average them or not. If you average them, the scales are comparable of SGD and GD. But if you don't average them, then they're not comparable. The gradient step is much larger, roughly n times the step of a single example times larger, right? So that's actually the next slide. So the technical computation of this is just taking expected values. Right? Why do we take expected values? Expected values are some operations that can be done on random variables that has some sort of underlying distributions. What's a random variable here? I thought we just had some examples. I thought I had a bunch of fixed points, right? I thought I had only those, x1s and xn's. But obviously, I can take them as random variables that come from some unknown distribution that's called p, right? So x is distributed as dp, in a sense, or we can just say p. Doesn't matter. So there is some underlying distribution of those examples that I'm selecting my samples from. And once I sample them, the sampled outcomes are those n samples. And hence, even though I don't know what p is, even though I don't know what the underlying distribution is, I can look at their expected values and compare them. Because in GD and SGD, the distribution will be the same. So taking expected value will give me a rough idea of the magnitudes of stochastic steps versus gradient steps. So let's just carry that out. I just plug in from the previous slide the expression for the gradient, take expectation. Again, expectation is a linear operation. And I have finite sum, so I can reverse the order of summation and expectation. When I take expectation inside, what I have is, in the end, is minus n times expected value of this expression, which is the step of a stochastic descent. So it turns out our intuition that we did on the board was indeed true. In expectation, the size of the mean size of a gradient step is n times larger than the mean size of a stochastic gradient step. Right? Just a simple observation that you can back with a little basic calculation. So what does this mean? If we don't average, and if we want to take an SGD step, we can maybe pick an example and blow it by n. So maybe it was this, and we can just blow this by n and take that step instead. Right? That's a possibility. I'm not sure if it's the smartest way to do this, but it's a possibility. Yes? Taking this step versus this step, you don't usually do this. It's just because stochastic steps, as you see, they're a little noisy. And if you blow them by n, they might take you to places where you don't actually want to go. Right? That's not, that doesn't give you, so ultimately, why do we do stochastic gradient descent? To gain time. Because time is a big constraint. I can't train huge networks with gradient descent. That would be lovely, but we don't have the computational power. That would take ages.
So if I take average in this way,
You're overshooting in weird directions. So each time, imagine them taking this. And it's going to be like this. Take this step. It's going to be like this. Take this step. It's going to go like this. So in n steps, you wanted to reach here, but you are God knows where.
so you are doing the line. So each one is a larger line.
Yes. Yes.
So it seems like the trade-off is, so if you have a fire that you're pretty confident that your fire is pretty close to the, let's say, the fire to the optimal point, then you probably would like to use the stochastic gradient descent.
Mm-hmm.
Small steps. But if you have an uninformed fire about, let's say, about this predictor, then you probably won't use, is that right, to use just the gradient descent? Because it's probably very far away, so you
Mhm.
can shoot further.
In my experience, I think it doesn't matter what prior you have, how far you are from the original minimum. If gradient descent is costly, you typically don't use it. Right. If you can't afford using gradient descent, and if you know your problem is usually nice and convex, which is what we had so far, then by all means go ahead and use gradient descent. It's much more stable, much more consistent in all cases. So, okay, let's take a look at the slide again. So it's just rewriting this expression of minus n times gradient. So it tells you what happens, comparing various steps. So the whole point of this detour was to get us back to the averaged loss. Right? So if I want to optimize the same thing with the same magnitudes of steps, I could use the averaged one. And if I have the averaged one, then my gradient step will be like this, and stochastic step will be like this. So they are going to be those small vectors. And the sizes of their vectors are going to be comparable. The SGD will have some noise, but their sizes will be comparable. And most of the times, I can't think of specific examples in which the total loss is going to be a better loss function, but most of the times you want to use the averaged one. You want to use the averaged loss. So unless there is a specific reason that forces you to use total loss, I would suggest using the average loss. And there are various other advantages of the average loss as well, and we'll come to that, yes.
Wouldn't be actually that solved by choosing or looking for the optimal step size in your both cases?
You could. So, you are saying I could always scale the step size by n and I could get the same thing, right? Then if you add regularization, then the scale of regularization will be different as well. But good question. You could. They're isomorphic. So the two problems are the same. I can scale either the step size or hyperparameters. That seems like it's the same thing. So it seems tautology. Why do I play with total loss versus average loss, right? The main idea of using average loss is the following. Suppose you have huge amount of data, thousands of data, and practically they repeat themselves. What happens then? You are double counting the same errors. What happens if you use the total loss? Or versus average loss? Yeah, right. So let's say you have the same thing. X minus. Let's say it's just x squared. Okay. Like our parameter is w. Let's say you have w squared, and you have whatever wx minus y squared. And you have two samples. You add this, wx2 minus y2 squared. And this is your loss. This is your total loss. And the average loss is 1/2 of the same thing plus 1/2 of the same thing, because you have two examples. So if you assume that x1 is x2 and y1 is y2, what happens? Your gradient step in this one will be just twice of the gradient step of this one, right? That's fine. What's your stochastic step? In this case, your stochastic case, so stochastic step of the average one is actually equal to the gradient step of the average one. In the above example, it won't be the case. In the above example, the stochastic step will be half the size of the gradient step. So this is like you have a parabola and you have another parabola on top of it. And instead of adding them up, you just average them, so it's the same thing, right? It gives you the same thing. So why is that important? So because if I have data that has similarities, then the stochastic gradient step will give me exactly the gradient step. So I will save time, and they will both have the same descent directions. So in this example, again, you can argue that if I scale everything by 1/2 in this first example, I'll get the same thing. But what if you have data that comes from two different sources. So all the parabolas are either here or there, and you add them up, and you have a little variation in between the two. So the data, let's say this is the data of zeros and this is the data of ones that you want to classify. And it's not perfect. It's, let's say, handwritten zeros and ones. So some zeros have this cost and some zeros have this cost. And in the one case, the handwritten digits have, some of them has this cost and some of them has this cost. So they're not exactly the same. And you have 30,000 such samples and you have a huge network to train. Calculating the gradient of those 30,000 examples will be painful. If you take the gradient step, if you are looking at the averaged cost, for the averaged cost, this problem of averaging over 30,000 samples will be almost exactly the same as just taking one from this, one sample from this, and one sample from that, and averaging over these two. It exactly gives you the same descent directions. So by just doing a little calculation, you save yourself time and computational power, and you have a method that's almost as powerful as a gradient descent. That's why in practice, yes?
Why you say computation power when you do that?
Because calculating the gradient of a sum of 30,000 of the same thing is 30,000 times slower than calculating the gradient of one term. Look, so in this step, since you don't know exactly what xi's and yi's are, calculating this amounts to calculating gradient of this n times, right? If you could just get away by calculating one term only, that would save you time by n times, right? They are huge. Weight matrix is huge, so you might not even have enough memory to collect all the gradients. Yes?
Why don't you, to avoid this problem of total and average, you take your gradient and make it square root of the norm?
Take your gradient.
You normalize the vector.
Which one? In the
You have for the total and the average.
yeah.
You take the gradient, calculate the gradient, then you normalize the gradient. Norm 1.
In the average one. Okay.
Yes.
So why would you normalize the gradient?
Because if you normalize the gradient, the total and the average one will be exactly the same. Because you normalize the vector.
But then, so if you make you're on different landscapes in the total one and average one. If you make the norms of the gradient the same, then you take different steps. So it's like in one example, you have an amplified world where a normal, an average person is like like Gulliver's gigantic world. You have to take gigantic steps to get to the place where you want to go. In the other one, you're in a tiny people world, so you have to take tiny steps. So you want to follow the path of the gradient. So what matters is not whether the gradient of this is comparable to the gradient of this, but what matters is whether the gradient of this is comparable to the stochastic gradient of the same landscape, or the gradient of this compared to the stochastic gradient of the same landscape. So fixing a function, logs function, fixes you the landscape. And that inherently has its own scale of things. Right? You're either in the gigantic world or the tiny world.
When you're calculating, when you're getting near the minimum,
Yeah.
the stochastic, the gradient tends to be, the norm of the gradient tends to be decreased.
Yes. In the stochastic case, it also decreases, but it's noisy. Why it's noisy? Because the sum of the two parabolas here is another parabola here. And you want to be around here in the minimum. And if you by chance sample a function from an example from the first one, the gradient will be large and it will throw you on the other side. And that's why in practice, in large scale problems, people do stochastic gradient descent with a mini batch. Not with mini batch size of 1, but with mini batch size of 10, 100, or maybe even more, depending on the problem. So here in this example, if I take random samples of 10 inputs, let's say I have 30,000 training examples, and I randomly select 10 of them, and look at the average. The average will be a really good estimate of the underlying function. Because I know I have, good chance of selecting almost equally from both classes by choosing mini batch size of 10. And since they're all very close to each other, the average of the two will give me something very similar to this landscape. So that landscape, by averaging, will be just maybe a tiny bit shifted version of it. And the stochastic steps will be calculated by the gradients of the shifted landscape. And the actual gradients will give me this landscape. So this is going to be a gradient step, and this is going to be a stochastic gradient step. But the good deal is that they are so much comparable. They are almost the same. So in this example, with mini batch size of 10, the stochastic steps will almost follow the steps of the gradient descent, which is a huge benefit. That's why it works in practice. Right. That's why average loss is much nicer. Yes. If you take 2, there is a higher chance that you maybe only select from the first class. You can do 2 too, because in the long run, if you keep selecting 2 all the time, some of them will be the averaged ones. So, for example, in the digit classification problem, and classical example where SGD works better than GD, much faster. In that case, you can take stochastic gradient, since there are 10 examples, you can take stochastic gradient mini batch size 100 or 128. That's the standard, I think, 128. Well, the trade-off is between computation time, what you can afford, because you want to increase the mini batch size, but you don't want to increase it too much to slow down the computation. Yes?
In the case when we're using, for example, mini batch with 10 samples, we have to average over 10?
Yes.
Okay.
And then take the gradient. And taking gradient of 10 summations is easier than taking gradient of 30,000 summations. That's the whole idea. It's actually pretty simple. So the idea behind SGD is that there is redundancy in data. Data usually comes in little clumps, and we select a lot of them. So you have to have lots of samples to train data, to train the system, train a machine. And if there's redundancy, SGD will work well because it will approximate the gradient very well. If it doesn't, I think in the homework, the case you had, most people had the trouble of gradient descent finding a better solution than the stochastic gradient descent. It's because you're doing mini batch size 1. So the gradient of this pulls you in a direction, the gradient of this pulls you in another direction. So you can't really stabilize here. It actually bounces back and forth here. You have to really wait a long time for the step size to diminish to a very low value to be able to see points here. So it seems like it's taking longer. It's because that problem is not the best showcase of SGD. Right. So it shouldn't mislead you. Yes?
If you take the average,
Yeah.
do you then still need to multiply your gradient by some step size?
Yes.
How does that factor in? Why do you still need to do that?
You always have to do that. Because if you...
Because you just want to make it even smaller if your step size?
No, you can take constant step size. That doesn't matter much.
No, I mean, like after you take your gradient, you maybe multiply by some like alpha. Like why do you do that just so that you're taking even smaller like step
It's,
sizes so you don't like overshoot the minimum?
So if you don't take anything, it's actually taking a step size of 1, right? Your step size is 1 in that case. So maybe 1 is too large of a step size. it will diverge. Or maybe one is a too small of a step size. It really, really depends on the problem. How do you put constraints on V? What's your X's and what's your Y's? If you normalize your data, if you pre-process and make all X's have expected value 0 and standard deviation 1, then it's different than having them blown up by a factor of 10. So you still need to do hyperparameter tuning. It's because you don't know the scale of your data. So it doesn't save you from hyperparameter tuning. Clearly, since the two functions differ by only a factor of 1 over n, once minimized, their minimizers are at the same place. Right. So on the domain, it's going to be the same point on the domain. The values are going to be different, the altitudes are going to be different, but the points are going to be the same. What happens if we add a regularizer, though? What happens in this case? In this case, they are not at the same place. Then in both cases, I just added a term that regularizes, that punishes large values of weights. Now the location is going to be a little different. Why is that? How can okay, let's ask another question. How can I change lambdas so that the two loss functions have their minimizers at the same point? Sorry? Minimum 0? What? Big lambda? Yeah, I can make lambda 0, but then I lose regularization. I want to keep regularization.
Lambda times n.
Lambda times n. So I can just modify one of the lambdas, right? So now the loss function depends on lambda. So the first one, let's explicitly write the dependency. It's lambda plus total plus and the other one is it's total divided by n plus lambda norm squared. So if I here, instead of plugging lambda, if I plug lambda divided by n, I also have lambda divided by n here, right? Then their minimizers are at the same place. But let's take a step back. Let's take lambda is fixed before I assign those functions. So I have these two. Which one, question is the last line, which one of those functions, once minimized, have the smaller complexity, smaller norm in lambda, in parameters w? Which one? Second one? First one? Second one, why?
Because it has higher regularization?
Yes, because it has higher regularization. Because we put more weight into regularizing norm of V than the emphasis we put on the actual thing we want to minimize. Okay. It's the end of the review part. So we have 10 more minutes for little kernel methods. Any same remark? This is not February 18, 2015. Not maybe. Any questions on the previous topics? Yes. This, so in general, let's say you have a function times, so let's just look at the first function, okay? What happens if I take lambda 0? Then there's no regularization. Whatever W star I find, I find. Why do I add regularization? I add it because maybe, by chance, I have a bad function here that doesn't punish large values of W, so it blows up. And it memorizes everything. I don't want it to memorize. It overfits, right? I want to prevent that. So in order to prevent that, in order to prevent this function blowing up, I add this term. Right? This term, what it does is that if I minimize the whole thing, I also want to minimize this. So it blocks growing, it blocks the growth of W. It blocks the growth of parameters. Right? So in the extreme where lambda is 0, this can be very large. This can blow up. What is the other extreme when lambda is infinity? Or very, very large. Assume lambda very large. Omega star will be almost 0, right? Yes, it's going to be 0, very close to 0. So what happens is very close to 0. Then it has, according to the previous definition, it has low complexity, which means it has low norm. Right? So what this means is that larger the lambda, lower the complexity. And that's how we derive this conclusion from the two different functions. Because the second one has larger lambda. Okay. Okay, let's go quick. X in this curly x, the curly x will be the space of texts, and x will be an example. You didn't see the slides yesterday, right? No, okay. So x will be an example of a text, and we're going to extract features. Features can be some keywords that can be extracted from the text, such as Android, that takes place twice, Google, that takes place twice, IO shows up once, and so on and so on. We'll come back to this text. So if we have two different texts, examples of texts, how do we compare the two? We want to find the notion of distance. We want to find the notion of similarity between the two texts. It can be identifying positive reviews from negative reviews. So if I find good keywords for positive reviews on Amazon, I can actually, if I can find the similarity notion between the two, by just calculating a number, I can say this is very close to a positive review. So it's supposed the other one that has an unknown label will be a positive review. And if the distance is too much, then I can assume that it's a negative review, right? You can do things like that. So you want to come up with a function that takes input as two texts, and it will output you a number, a real number that will determine how close they are. Various ways to do that. Let's say we have the following two texts. They seem to have come from similar contexts, and I can look at number of occurrences of various keywords. Now I have some feature vectors. I extracted a vector of dimension 7 here on one side and on the other side for both texts. Now I'm going to compare them. It seems like their similarity is peaked in the first two elements, but how can I create a rigorous notion of comparison? Let's say I normalize my vectors. What I do is I just take squares of all the elements, take the square root, and divide every element by that, which gives me a new vectors as the following, which is just a normalization. So they have the same sizes, right? So they become comparable now. Now what I can do, now I have two vectors. They're normalized. I can take the dot product of them. I can take the inner product. The inner product, remember, it gives you the angle between two vectors. on a given space, on a given inner product space. And I checked the inner product. Inner product turns out to be 0.85, which kind of indicates high correlation, right? So, the two texts that are originally started with have some similarities that's beyond random. It's a good indication. Okay, it seems like inner product of features. Features, remember, they were extracted by number of occurrences of certain keywords. In this case, inner product seems to be a good kernel. So a kernel is something that takes two inputs and spits you a number that roughly compares and measures the distance between two objects. Okay. It's a little reminder, some linear algebra. An inner product. So before we go any further, how do you know the relationship between inner product spaces, norm spaces, and metric spaces? So we want to create a notion of angle and distance. And according to this equation, this first equation here, we have a notion of angle because we have this cosine theta there, right? We know that it's related to, it just measures an angle. The theta has to be an angle between two vectors. But it also has a norm. It has norm of v and norm of x. So does it mean that every inner product space has a norm in it? The answer is yes. It indeed does induce a norm. So if I have an x in the space, and if I have an inner product defined, then I can define a norm induced by the inner product as x dot x, right? This means that every inner product space is actually a norm space. And in turn, I can use the norm to define a metric space. This means every norm space is a metric space. So if I look at the set of all spaces that are inner product, they are going to be the smallest because inner product implies norm. So those are going to be norm spaces. And this implies metric, which is even larger. And the reverse relation is true. Not every metric space is a norm space. Not every norm space is an inner product space. So why is this important? Yes? Metric space is the space where you have a notion of distance. The only thing you have in your hand is a notion of distance. There are assumptions of all of them. We don't have to go into this. The only thing we need to understand when it comes to separation of those spaces is that metric can be a very vague notion. As long as you can describe a distance, pretty much, it's going to be a metric space. But it won't have the rigidity of norm. Norm is a little more special. Norm gives you certain scaling properties, for example. If you take a vector, multiply it by 2, then its norm should be twice as much. You don't have to have that in a metric space. So norm space is more rigid. What extra thing do you have in an inner product? Let's answer this and we are done. So norm space is a little rigid. It has distances that scales with the constant proportionally. And as you said, the inner product space has the extra notion of angle. So not every norm space has to carry out the notion of angle. But an inner product space, on top of being a metric, has a distance and has rigidity of norm. On top of everything, it has the notion of distance, notion of angles. Right? That's why we have the first equation there. And that's why we can take two texts and look at the similarities. That's why inner product spaces are going to be the suitable spaces to work on kernels. And more on kernels will come in the next class. Thanks.